Okay, so welcome to our first video on limits and continuity, and yeah, we're just gonna get started. This video is mostly gonna try and introduce the concept of limits and continuity with a lot of simpler limits, but then we'll go into some more typical problems on limits that you'll see on the AP exam towards the end. Okay, so this first one is just sort of like spamming a lot of different limits here. So we've got graph of r of x, which is this graph right here, and we're going to try and find all these limits. Fun. So each one of these letters is a point on either the x or the y axes. So yeah, and then horizontal, these dotted lines will indicate asymptotes, either horizontal or vertical. So, okay, so let's start with x approaches infinity. So what does this really mean? Well, we're sort of like going towards positive, x is going to positive infinity. That's literally what this notation is trying to say here. And so where is positive infinity? That's going to be that way, right? To the right. So just as we go to the right infinitely, where are we going to go? And so we go here, and then we eventually settle on some sort of horizontal asymptote at y equals f. So that is where the limit is as we go to positive infinity. Okay. So now let's do negative infinity. And so negative infinity is a similar concept. X is, as x goes to negative infinity, where does r of x go? And so we're just going here. Note that it sort of goes here and then it jumps up there. It's continuity. And okay, so we also appear to be settling on this horizontal asymptote of, which is also y equals f. So the limit is, the same as we go in both directions. It doesn't have to be the same. There will be some examples where it won't be, but in this case it was. Okay, so a plus. So what does this plus mean? It means we are approaching a, which is right there, from values that are greater than a, from x values that are greater than a. So where are the x values that are greater than a? Right here. So we're approaching a, so we got to go this way. And so, okay, where does r of x go as we approach, like that, as shown in this arrow? So, kind of going, it appears we're going to go down, like, kind of forever as we approach a. So that means that limit is going to be minus infinity. Or you can say dne. So dne is does not exist. And the reason that you can, kind of say both is because a limit technically has to be finite in order to exist. So if it's infinite, then you can also write dne. Okay, a minus. So let's see, where from which side? So this time we're approaching a from x values that are less than a. So that's this part of the x-axis, and we're approaching a. So we're going to go like this. And where are we going to go? Well, it's going to be up here, right? And that's where r of x is now. So we're going up, and we're just going to go up forever as we approach a from the left side. So this limit is going to be a positive infinity, or again, you can also write dne. Okay, so limit x approaches a. So the big thing about limits, which hopefully you take away from this video, is that if you're approaching a for some, let's just use r of x, right? In order for this to be anything, in order for that to exist, right, it needs to equal the left-sided limit, which also needs to equal the right-sided limit in order for that to exist. So basically the left-sided limit has to equal the right-sided limit. in order for the limit to exist. So is that the case? Clearly not. So it just does not exist. Okay, x approaches 0. Okay, so as x is going to 0, where is r of x going? And I mean, it's going same place from both sides, so it's pretty clear it's just going to be 0. Okay, next problem here is b plus. So x approaches b plus. So remember, it's x values that are greater than b, and we're approaching b from that side. So we're going to approach like this. And r of x, where does r of x go? It appears to go down to minus infinity. So that's going to be the answer there. Or we can write D&E. Okay, b minus, same idea, or similar idea. So we're approaching b from x values that are less than b. So we're going to be approaching like that. And where does r of x go? It just goes up to positive infinity. So that's going to be the limit there. Okay, x approaches b. So clearly the left and right hand limits are not the same. So that limit cannot possibly exist. X approaches c. Okay, so where is c on this graph? It's going to be here. And so we have to check, the right and left sided limit as we did for the previous ones. So the right sided limit, right, coming this way, it's going to go down all the way to j. So we can write over to the side here, limit x approaches c plus, r of x is going to be this point j. But if we try and find c minus r of x, what is that going to be? Well, we're coming from this way, and so right, where does r of x go? We can see it just skyrockets up to positive infinity as we approach c from the left side. So that means that right, these are not the same, so that limit also cannot exist. Oh, this is so sad. The limits are either 0 or infinity, or does not exist. Okay, so x approaches d. So okay, let's clear some of these markings here. So where is d? That's this point. And once more, we do have to check the left and the right side. So the left side, we're going to come in, so we go like that. And the right side, so it looks like we are going to approach the same point. Where is that point? Maybe hard to see, but that is point k, or the y value of k. So k is the answer to that limit. Okay, finally, x approaches e, r of x. Where is e? Okay, e is right there. So an important thing to note here is that e, like r of e, is actually just I, right, as we see right here. But that's not going to be what the limit is, because like all the other values of r that are like super duper close to e but not exactly e are huddled around over here, huddled around f. And the right and left side limits are going to be the same, so actually that's going to be f and not e. So this is an important thing to note, is that the limit may not exactly be the point at which the function is defined, but the limit can still exist. But so r of e, as we covered earlier, is going to be I. R0, in this case, R0 equals the limit to 0 as x approaches 0. But it is actually going to be 0. And then b, so r of b, r of b does not look like r has a value actually at b, because there's sort of an asymptote at x equals b. So that's just not going to exist. R of d, okay, d is right here. So r of d is, once again, this is going to be the same as the limit, because r is continuous at around that point. So r of d is just going to be k. And if you didn't understand what I meant by continuity, don't worry, we'll get to the formal definition of continuity eventually. So yeah, we did all of these problems to sort of introduce the idea of limits, and so now let's see this idea show up in a lot of different ways. Okay, so limits with the table. So function h is continuous, right? So, okay, what does continuity mean? I've been referencing it so much. So basically, if you're continuous at some point, let's call this k, because that's not usually used. So if you're continuous, if you want to be continuous at k, right? So the limit as you approach k for some function f of x, right? It has to exist, first of all, right? And then f of k also has to exist. It has to be some sort of finite value. And the other probably big thing is that the limits and the value have to be the same thing. So if you meet all these, if a function meets all these three conditions at a certain point k, then f is considered continuous at k, and if f meets these conditions for all x, right, like a polynomial, like, a polynomial might look something like that, then, we can say that the function f is just continuous in general. So what this implies is that it follows these three conditions for any value of k that you want. Okay, so that's what continuity means. And then we're looking at decreasing for x is greater than 0. Okay, so these x values are greater than 0, so that will apply in our table. Which of the following values best approximates this? Okay, so h is continuous. So the thing is, we can use this. Here, I'll put this formula off to the side here for composite limits, where if we want to find the limit at some point at f of g of x, right, let's say, then if we know that f is continuous, then we can sort of just like shove the limit inside. And that's the best way that I can describe it. Shove the limit inside, and you can just evaluate this and you'll get that limit. So we can apply that. Oh, but remember, f has to be continuous. That's important because we'll see later that this formula doesn't always work. So, okay. Limit x approaches 2. So if you want, you can like take this constant out, right? Because that is a limit rule or limit property. You can shove constants out. And this is a common theme in calculus. You can also shove constants out of derivatives and of integrals. So, yeah. Okay, and cosine x is continuous, so we're going to apply the formula that we just wrote down. Okay, and so 3 cosine. Okay, now we've got to approximate this, right? So what is x approaches to? So from the right, those are from x values that are greater than 2. So maybe 2 somewhere there. And so these are the values that are approaching this way. And so where do those look like? Oh, they're increasing, right? They're increasing towards maybe 0, right? And that makes sense. As you're going this way, it would increase because the function is decreasing. And now let's look at the other way, right? So the right side, we're going to approach like this. And, it also looks like that we're approaching towards 0 or decreasing towards 0 from the right side. So we can conclude that the limit would probably be about 0. Right, they're asking for an approximation. So now we're just gonna, evaluate this. So 3 times 1, or just 3. And so we get D for this answer. Okay, so this next one is fun. It's a calculator problem. So, okay, let's read this here. So let f be defined by that ugly function. How many values of v exist such that limit x approaches v is minus 7.2? Okay, so one important thing to note is that f of x is a polynomial. And so why is this important? So this means that f of x is continuous because all polynomials are continuous. So yeah, if you want like a little diagram here, here's continuous functions, and then here are polynomials, and then this is f. So yeah, all polynomials are continuous. Okay, so that means that, right, for all v, the limit as x approaches v f of x is going to be f of v. So we can really just find out, how many times is f of v minus 7.2. So, basically we have to solve this equation. It's 5.6 minus 7.7, and then minus 4.97 equals minus 7.2. So we have to solve this, and then the values of x that we get are the values of v that we're going to want. Okay, let's pull up this calculator here. And so you can go to the graphing area with the y equals button right there. And then now we are going to put in our function. So 5.6x to this, and then minus 7.7x to the fourth, and minus 4.97. Okay, and then we're just gonna also plot the line y equals minus 7.2, and then write the points where these intersect will ultimately be the values that we want. So I'm gonna push the graph button, and right now we're in zoom standard. So let's see what we get from zoom standard. Is usually a good place to start for graphing, but like if you don't know what I'm talking about by zoom standard, you go to zoom and then it's number 6, zoom standard. So those are just different like zoom levels for your graph. So if we expand this, if we expand this a little bit, it may look like there are 2 values, right? There's one right there and there's one right there, but it is always a good idea to set your window and set it like closest to the areas of intersection, closest to the areas of action, so that you can really make sure that you're getting the correct picture here. So I'm going to use this little like point thing that I can move around to sort of like guide my window. So maybe I'll go from minus 1.2 all the way to let's see, minus 1.2 to 1.9 on the x side. So let's see, just spin this here, minus 1.2 to, oh sorry, x min is up there, so minus 1.2 to 1.9, and then our x scale, you're not gonna ever need to touch x scale. And then now let's look at this again, give it some time to load, and then we'll adjust the y. You may want to just do both x and y at once, just to save time. But you can already see here that it looks like there might be something fishy going on with that second intersection point. So let's confirm our punches by. Okay, so minus 8.8 on the y to minus 3.6. So go down. Okay, sorry, this window is not cooperating. Okay, minus 8.6 to 3 point something. Kind of forgot. Okay. Alright. Hopefully your calculator doesn't take this long to graph simple functions. It's kind of a mobile emulator, so it's taking forever. So yeah, now we can sort of see a little clearer that there will be 2 intersection points there. We can try and verify that by going even closer, right? So from 0.8 to 1.3 on the y. So on the x, I mean. So 0.8, 0.3, So we're just looking at the second intersection point. This is why you never trust graphs by their face value. Always be skeptical of graphs, because the College Board will try and trick you with a graph on the AP exam. So yeah, you can sort of zoom in like even further if you wanted, but there are actually two right there. So okay, so yeah, there will be 2 plus the 1 that we found before, so there'll be 3. So yeah, basically this question was a little extreme in that you had to zoom in all like an absurd amount, and you probably won't see something this extreme on the AP exam, but the point still stands. You do have to check your window, because they will trick you on, you know, dumb things like that. So yeah, just keep an eye out. Okay, graphical limit. This one's tricky. So, alright, so let's see here. Piecewise function, okay, 2 line segments, so 1, 2 line segments, and a semicircle. Okay, that's your semicircle. For that, okay, here's -5, here's 4. Oh, you can't see that, but let me zoom in. Okay, yeah, I don't know, this is kind of hard to see, but those are, trust me, those are the x values. And then find that limit or determine if it does not exist. Okay, so on the AP exam, right, whenever you have a multiple choice question where it's D&E, right, does not exist, does not have an answer, always be really careful before you pick the answer, because like I'd say a good 80% of the time it's a trick and they're trying to get you to pick this answer, you know, so that to trick you guys. So yeah, this is usually a trick answer. So let's see, but you know, maybe it's not. So let's see. Limit x approaches 0. Okay, so one thing right away, f is not continuous right there at x equals 2, because the limit doesn't even exist, right? The right side and left side are completely different. So since f is not continuous, you cannot say that this limit is going to be f of the limit as x approaches 0, 2 minus x squared. Right, this doesn't work because f isn't even continuous. So, okay, what to do? Well, let's just look at this 2 minus x squared, right? Because where that function goes will sort of determine how we approach f of x. Maybe if I explain more, it'll make more sense. So, okay, here's our little graphs here. Oh, x and y. So 2 minus x squared, what does that look like? So I know, you know, it's going to be downward parabola. It's going to have, right there. Just draw that. Okay, so this is like generally what this parabola looks like. And we're approaching 0. So from the right and from the left, right, we are approaching 0 from the bottom. We are approaching 0 from y values that are less than 2. Now, does this sound familiar? Right? So the y values of this function of 2 minus x squared are actually the x values of f of 2 minus x squared, right? Anytime you say f of something, right, this is your input. So this is no exception, right? So the reason why it's important that the y values are coming in from less than 2 is because that means it's like the x values of f are coming in for values less than 2. So we can rewrite this, right? Limit x approaches 2 minus, right? This is exactly what we were doing over here. We were evaluating one-sided limits, except we were saying, you know, we were going from x values that were less than a certain point. Except, you know, this is the same thing, right? 2 minus x squared is going to be a, you know, x value, or maybe more clear might be the term input, but it's going to be an x value or input to this function f of x. So that's why we can write this as a one-sided limit x approaches 2 minus f of x. Right, and that's pretty easy. So 2 minus from values that are less than 2, and approach like that. Okay, so that's 2 comma 3. That's the point that they give you right there. So the answer is going to be 3 because it's actually a one-sided limit. So yeah, be careful with composite limits. They may trip you up like this. Okay, so I've included we're going to be doing a fair amount of these piecewise continuity problems because they are very, very common on the AP exam. You will probably get at least one. So yeah, let's see. So find k so that this is continuous for all x. Okay, so what does continuous mean? Let's just recap. So for f of x at some point x equals c, okay, go back to textbook and use x equals c. Right, that has to be true, and both of those must exist. Okay, great. But if it's continuous for all x, right, and that means whatever c we choose, this has to work. So let's see. We've got a piecewise function defined for everything but 4, right? And then we've got something for 4. So maybe let's look at this a little closer first. So x squared minus 16, we can factor that out. It's a difference of squares, right, over x minus 4. And one important thing to note is, as it stands right now, like if this was just f of x, which is not, it's that. But if this portion was just f of x, then f doesn't exist at x equals 4, right? Because you'll get a 4 minus 4 in the denominator, and you'll just go to 0. But there's an x minus 4 in the numerator, so these will cancel out. So what does that mean? So f of 4 doesn't actually exist. But if we were to graph this, right, you'll find that it's going to be like a line. It's going to look like x plus 4, and it is pretty much x plus 4, except at x equals 4, where there will be a hole right there. That's the word for it. So a hole, because the limit exists at x equals 4, but f of 4 does not actually exist. So, okay, but this isn't really f of x, right? This is f of x for everything but 4. But luckily for us, they've given us a special y value of k. So we've got to place k in just the right position, right? Maybe just imagine sort of raising the hole until you perfectly fit the hole, right? And you get to the right altitude where the limit as x approaches 4 f of x equals f of 4, which, has to equal k, right? F of 4 has to equal k because of the way that this function was defined. So, I guess we should start by figuring out what the limit of x approaches 4 is, and we've already done the hard part. So I'm going to rewrite this in terms of limits. X approaches 4, x plus 4, right? So we're going to cancel. Then we're going to have x plus 4, and now this is pretty easy, right? So x plus 4 is a continuous function, so we can just plug this in and get 8. Okay, so the limit is 8. So I'm going to erase this. Hold on. Eraser. Please work. Okay. So, So we know now that, right, this limit is now just 8. So that means, right, that f of 4 has to be 8, and that means k has to be 8. Oh, well done. So we've just figured out what k is. K is 8. And this way, right, it is continuous for anything but 4, because as long as x isn't 4, f of x is just going to be equal to x plus 4, which is a polynomial, so it's continuous. And then at x equals 4, we made sure it's continuous by, plugging in the hole, by choosing the correct value of k so that it's the same as the limit. Okay, so that'll be all for today's video, and I will see you guys next time.